So I would like to thank Edith and the organizer for giving me the opportunity to speak to what is for me an unusual audience, because I'm more of a stellar dynamicist than expert in turbulence, as you will see. And so I'm going to try to argue that gravity is playing a key role in setting up and maintaining thin galactic disks. And here, unlike what Bruce told you yesterday, I'm going to be talking about stellar disks. Okay, so and I'm trying to argue that, in fact, galactic disks can emerge in a relatively chaotic universe. And I remind you that the emergence is defined as the arising of novel and coherent structure through self-organization in complex systems. So the galactic disk is going to be a somewhat complex system, but I'll break it out for you. And on the way, I will show that the fact that the disk is self-regulated will lead to also self-regulating star formation, and this self-regulation will be driven by gravity rather than subgrid physics. And to be a bit controversial and catch your attention, I'll try and argue that the main ingredient, which is for some reason, which I don't really understand, has been mostly ignored for the last 30 or 40 years, is that the wakes are playing the key role rather than the turbulence. Okay, so that's for introduction. So context. As Bruce mentioned, galactic disks tend to be very thin. This is true also at the level of the stellar component. And it's kind of unexpected that in a very chaotic universe, hierarchically forming, these structures spontaneously emerge, because you need to form stars in a plane and you need to maintain them in such a plane for half a Hubble time at least. So just to remind you, you've probably encountered examples of emergent processes through your studies or watching the sky or the sea. Typical examples are flocks of birds or schools of fish, and maybe more spectacularly, snowflakes at the temperature corresponding to the transition between water and ice, or another example of emerging complex structure which is not encoded in its component, the molecular water, the water molecules. And a typical characteristic of these emergent processes is they tend to occur near phase transition in open dissipative system. And so galactic disks are exactly in this situation. They're possibly transitioning to being unstable. And in the universe, they are being fed continuously with gas, which they dissipate. So they correspond to this regime. If some of you haven't seen this amusing video on YouTube, an example of emergent process would be a bicycle, which the way bicycles are designed, if you just throw them onto a slope, they will typically continue to work, because as they fall, they turn, and as they turn, they fall. So this is an example of self-regulation by gyroscopic effect. And there is some analogy with the gravitational system in that the way it works is that the bicycle pumps free energy from the gravitational potential of the slope, and it self-regulates by by accelerating and correcting departure from equilibrium more and more rapidly. So going back to galaxies, the synopsis of disk emergence can be characterized in 3 sentences. Why do disks settle? Because they get closer to marginal stability. Why do they get closer to marginal stability? Because they build up a tighter control loop near marginal stability via stronger and stronger wakes. And how does this impact settling? And because the wake also stiffens the different component of the disk, which leads to a more tightly bound and aligned disk. This has implication. The fact that this process is happening, which is a dynamical process, has implication in terms of the steadiness of star formation in the secular regime, where one is dominated by the stellar component. And it leads to the observed scaling laws that you're all familiar with, and it explains why these scaling laws are tight, which is the counterpart of the tightness of the dynamical.
Christophe, what do you call wake?
That's my next slide. or maybe the one after. just to say, if you just after finding that galactic disks occur in the universe, I guess you need to look at quite recent cosmological simulation. They seem to be an emerging structure. So if you're just interested in matching the data, well, I guess you're good. Here I will try and explain why this is happening and why it's interesting, and why the fact that it's happening explain other correlated properties. Am I cheating? No, I'm cheating a bit. It's a bit further. But I can answer you now. So wakes is like I give a list of 5 or 10 different words for wakes. So you can think of them as polarization, as dressing, as swing amplification, spirals. It's the fact that the self-gravitating disk is highly responsive to any perturbation, which will strongly amplify. So that's the wake. And it's not something I invented. I mean, it's in all good books, starting with galactic dynamics or before. So I'm just reminding you that this is happening in disks, and for some reason, it's not really taken into account in the way we explain disks. It's taken into account by the simulation, of course, but it's not typically discussed in those terms. So let's zoom out on the circumgalactic medium. In the circumgalactic medium, the gas and the dark matter are not doing exactly the same thing, which is kind of obvious if you look at the Pourquoi ça fait ça? J'ai appuyé longtemps peut-être. If you look at the distribution of the gas and the dark matter, it's much more sharp for the gas component in the CGM. And the main reason is that the gas doesn't have the same dynamics as the dark matter. Every time it encounters a component of the cosmic web, the gas shocks, whereas the dark matter just shall cross. And so because they have different dynamics, they end up having a different distribution in the vicinity of a given galaxy. And so this has an impact in the sense that the cosmic web, the filaments are actually like motorways which are controlling the flow of the gas towards the central galaxy. And because the cosmic web is less dense than the galaxy itself, its typical dynamical time is longer, so it provides some steadiness to the way the gas is infalling onto the galaxy. If these walls and filaments are surrounded by voids of different importance, they will typically be pushed by the more massive void, and this will induce some transverse motion for the filamentary structure. And so from the point of view of the incoming gas, as seen from a galactocentric point of view, this advects coherent angular momentum, which is steady because the cosmic web is moving slowly. So this is an example of top-down coupling between the large scales, which don't move a lot, and the galactic scale, which move more rapidly. So disk reform, because the large scales are large, dynamically young, and partially anisotropic. There's this cosmic web around. Questions? No. And this induced persistent angular momentum advection of gas along filaments, which stratifies so as to rebuild the disk or build the disk. And so one needs to revisit the spherical cow galaxy formation model to account for the fact that it needs to be rigged by the filamentary structure, because this filamentary structure has a strong impact on angular momentum acquisition. And this is relevant because the shape of the initial power spectrum of lambda CDM is such that this filamentary structure will form before or at the same time as the object itself. Okay, so we're in a situation where in the CGM we accumulate cold gas, which is going to allow us to build a reservoir of free energy to fuel the thin disk emergence, because we are bringing a coherent gas, and the galaxy itself is realigning itself with respect to the CGM. So to sum up, from the point of view of the initial power spectrum, we have a bottom-up hierarchical clustering of structure formation for the dark matter. But in parallel, we have top-down nonlinear mode coupling induced by the fact that the gas is flowing along the cosmic web, which is guiding the gas from the large-scale structure onto the CGM. And to anticipate the second part of my talk, The same thing will be happening once again at the level of the spiral structure inside the galactic disk, where again the responsiveness of the disk will trigger stellar transient spirals, which will gather the gas and induce a cascade leading to star formation. So again, top-down causation induced by shocks happening on what this time would be the large scale, which would be for you kiloparsec scale, so inter-arm scales, down to wherever stars form, which is the domain I don't know about and I'm here to learn about. Okay? So to repeat somewhat differently, we are considering a given scale, which is the Galactic scale, which has a time scale of unit 1, let's say. It's embedded into a larger scale, which has a longer dynamical time, and it's containing smaller scales which are beating faster. And so because of the fact that these different scales have different time scales associated to them, the coupling, the nonlinear coupling induced in nonlinearity of structure formation will not impact our galaxy the same way. We inherit stability from the large scales, and we're impacted by stochasticity from the smaller scales. This is playing a role, and it can be modeled by a stupid toy model where you consider a sourced harmonic oscillator, cubically sourced harmonic oscillator, and you assume that the environment is beating at a different frequency. So big omega is the frequency of my system, little omega is the frequency of the environment. And if I compute, which is given here, what is the response of this system, I find that if I'm beating at a smaller frequency, so if I'm impacted by larger scales, then it impacts my mean, which is the red curve. And if I am beating at higher frequency, so smaller scales, I'm mostly impacted by the RMS, which is another way of saying what I just told you. And what's interesting on top of that is you see these resonance happening. So what this means is for such systems, the coupling from smaller scales to intermediate scale is going to involve not just the RMS of the fluctuation, but the power spectrum of the fluctuation excited at the resonant frequency of the system. So this is generic, and this is true in particular for self-gravitating system. But what's interesting is that if this self-gravitating system is cooled, there's an extra factor which is going to play a huge role. The fact that these fluctuations are going to be dressed, or a wake is going to be created, and this dressing will be typically quadratic in the gravitational susceptibility of the system. So you should think of this net effect of how small scales are impacting a galactic scale as some kind of, if you want to use serious words, renormalized effective field theory, because you're impacted by small scales through their power spectra, and this power spectrum is being boosted by the self-gravity of the system. Okay, so now back to our galaxies. We have a given stellar disk, which is impacted by a stabilizing effect, which are heating the disk, meaning making the disk more eccentric, and destabilizing effect, such as new stars being formed on circular orbits, which are cooling in a dynamical sense the system. And so it has to deal with these two competing effects impacting its long-term stability. So we have a three-component system, which are coupled twice by gravitation. There's the cosmic wave and the CGM on the one hand, and the interstellar medium on the other. The CGM plays the role of a reservoir which is fed by the cosmic web, as I've explained to you. At the level of the disk, the stellar disk will converge towards marginal stability, which will accelerate the control loop via wakes, as I will argue again. And because of this tightening of the control loop and the wakes, I get stiffer coupling between the different components. And that's it. No. And because these swing amplified spirals are triggering star formation, I'm going to generate a link between properties of the star formation on the one hand and property of the galaxy as a whole through this driving process of swing amplification. And so this generates tight scaling laws. Okay, so that's the famous slide I promised Edith, so it wasn't quite the next slide. In my mind, it was the next slide. But so wakes are transient spiral waves, weakly damped mode, gravitational susceptibility, polarization, dressing, swing amplification. Depending on the field, people use a different term, but it's all the same thing. And because I'm interested in the long-term evolution of a galaxy, and its stellar component in particular, what I'm interested in what's happening to the orbital structure of the disk. So what I'm after is the short-term and the long-term evolution of the distribution function of stars within my galactic disk. And I want to convince yourself that it can self-regulate towards becoming thinner. So wakes, when you put, there's a nice result by Agris-Kalnight from 74, something like that. When you put a mass of 1 into a constant rotation curve called Mestel disk, you generate a wake which is of a mass which can be as high as 150 if the disk is sufficiently cold. So what this means is any perturbation which will be imposed by either external or internal properties of the disk will generate these strong transient wakes. And the important point for me is that these wakes are inducing correlation on very large scales within the disk. And so this allows the system to react quickly to perturbation, in that it's gravity which allows you to propagate information very quickly. This is important because if you try to do feedback with baryonic processes which don't involve the long range of gravity, it's sometimes quite difficult to make very different scales talk to each other so that they can self-regulate. Here, gravity is long range, and wakes provide coherence through the whole system. I'm not speaking too loud? No, okay. So these, to give you an example, this is a simulation of a massive cold disk, and this is the corresponding gravitational susceptibility, which can be computed. So it's a measurement of the boost induced by the wake as a function of eigenfrequency, so the rotation rate of the instability and the growth rate. And if we do the linear response of this system, we find indeed that we get a mode at the right frequency in terms of how it grows and how the disk is the spiral wave is rotating, and we get the right eigenvector. So we can predict, given a property of the galaxy as a whole, what is going to be the spiral response of this system in a unique manner. And so this is a way of propagating properties global to the galaxy to the local property of the spiral arms. Now, real galaxies are embedded in a dark halo, which means that the unstable mode becomes a weakly damped mode. But we can also compute its characteristic. And once again, the property of the mode define the shape of the spiral response. Okay, thank you.
What controls the width of the spiral arm in your simulation? You're simulating things, right?
No, this is a linear response. I'm doing the Kalnight matrix response. What controls the wake is the property of the underlying distribution function.
No, I'm talking about the width of the spiral arm.
Well, that's not an easy answer to, well, that's not easy. But the fact that it's not easy, it's interesting because it means it's a global property. For instance, if there is a bulge or there's no bulge, the spiral structure will be different. If there's a big halo or no halo, it will be different again. Okay, so qualitatively, we have these damped modes, which are generic. Most galactic disks are actually stable, but they're very susceptible, which means that any perturbation is going to be strongly amplified by the presence of this damped mode. And the fact that we have a damped mode means that the dynamical time is shortened by the gravitational susceptibility, which is almost equal to 0, because it would be 0 if it was on axis. And similarly, the fluctuation of the potential are addressed by the gravitational susceptibility. So this was the frequency domain explanation. This is the time domain explanation, but it's exactly the same thing. The existence of this damped mode corresponds to the fact that any perturbation is going to be strongly swing amplified, but in a transient way. Eventually, the spiral disappears. Okay, so this was like the linear response. Let's move into the heating regime. So what happens when you try to compute the net effect of many such spiral response over a long time scale? What does it do to the underlying orbital structure of my galaxy? So this is the domain of kinetic theory as was presented by you? Sorry. And so the net result is that the rate of diffusion of the orbit, which would be the analog of the orbit of the diffusion of ink in water, is going to be given by the power spectrum of the fluctuations, right? And so the only difference being in water, the hotter the water, the faster the diffusion. In galaxies, the colder the disk, the faster the diffusion. So this is an example of diffusion happening in a galactic disk, where if the eccentricity is increasing, as in yellow, the diffusion in the eccentricity direction, or the diffusion in the guiding center direction, and that's taken care of. I won't repeat what has been said yesterday about how you derive such equation, but basically you can make prediction for the average behavior of maybe 1,000 galaxies, and it's going to be related to the square of the fluctuation encoded in the distribution function and the corresponding Hamiltonian. And because this goes like the square, and because they're out of phase, it actually pops a power spectrum of fluctuations. And because these fluctuations are dressed by the gravitational response, the rate of diffusion is going to be quadratically dressed by the gravitational susceptibility. So this means this is a huge impact. The fact that your disk is cold is going to greatly accelerate by a factor of 1,000 or more the way that the orbital structure is diffusing if you don't compensate, if you don't form new stars. So this is an example of us measuring, making prediction for the rate of diffusion. Here, the change of the distribution function as a function of time. And two important features. The factors here, when it's de-dimensionalized according to the number of particles, is huge. The factor of 1,000 I've been telling you about. It's recovered. And the diffusion goes along preferred direction corresponding to the resonance between where the fluctuations are happening in time-space and the frequency of the imposed by the underlying mean field. This is the same while averaging over 1,000 simulation, and you see that you get a good quantitative match. I'll just skip that, but it's to highlight the fact that there's a direct correspondence with the direction of diffusion and the position of these damped mode that I've presented to you here. So it's really the underlying physical structure of the galaxy, which is defining how the system heats. And let me say a few words now about the cooling process. So while my spiral is unwinding, gas is being collected, okay? It's being collected into the spiral arms, and while the spiral structure itself is stable, the gas will become denser and shock and induce a cascade leading to star formation. So the process does not depend on the details of the property of the gas because it's driven by the stellar component, and the stellar disk itself remains stable. So you get recurrent, effective or ineffective, depending how you want to phrase it, star formation, which is induced by the fact that every perturbation triggers leading spirals, which are unwind into trailing spirals. And that's what I just said. And so if you do a sharing sheet, gas plus star swing amplification calculation, you find that even if there's a small amount of gas, 10% here, you can get very strong swing amplification in the gas component, which is going to trigger your cascade in the right scale to induce star formation along the cascade. This has been seen by Kim and others back in 2007. I understand that this is maybe superseded by more complex models, but the essence of the process is that the unwinding of the gaseous spiral leads to shocks and the onset of gravitational collapse. This is a modern result showing that it's really the presence of the spiral which is responsible for gathering the gas, not the underlying star formation efficiency, which is changing in spiral arms. So it goes in favor of sustaining the model where it's the large-scale dynamics which is driving star formation. And now I need to accelerate a bit, I guess. Yes. So let me accelerate. So these are order indices. So emergence is the process where, because of the wakes, the interaction between the stabilizing effect, the cooling, and the heating gets strongly accelerated. And because it gets strongly accelerated, the system can self-regulate in a thermal state, in a dynamical stellar component thermal state. And I need to move to the end, I guess. So these are evidence for why this is true, and I just skip them. Just to give you an example, well, or you give me 10 more minutes. No, what is true? I should say one thing. It is true in the sense that I wrote for the 5th time an ERC this summer, spent 2 months on it. But this time I followed the instruction, which is that I needed to put into context my work compared to what has been done. And so I looked at what the implication of this model should be, and I found quite a few evidence. One of them being the tightness of scaling laws. So I hope you understood that this mechanism creates a connection between, on the one hand, how efficiently you form star formation, and on the other hand, the global property of the disk, dark halo included. So this explains naturally why you have tight scaling laws, because these scaling laws typically relate the efficiency of star formation to macroscopic property of the disk. And the more the system self-regulates, the tighter the scaling law. And this is exactly what is seen, for instance, in recent Tully-Fisher residuals, where the residuals in the Tully-Fisher relation are directly related to how thin the disk is. So this was not a prediction of the model, it's a consequence of the model, and it seems to match really well this kind of modern data. And now I'm going to go to the end. This explains why you get the tightening of the disk, but I guess you won't know. So let me finish on this. We're in a situation, because this brings kind of a new equation in the game, which I think should be of interest to all of us. We're in a situation where we're not just forming stars out of gas, we're accelerating the conversion of gas into star because there are stars. So I can write a kinetic chemistry equation for this transformation, and this leads to a logistic equation, which is of this form. You can think of it also as the Taylor expansion of star formation versus feedback, if you want, but it leads to the same thing. But if you now add the fact that you also have orbital diffusion, then your logistic equation becomes reaction diffusion. And if you add wakes, then this reaction diffusion is being quadratically accelerated by the wakes. So it means it's a very robust attractor for galaxy evolution. So galaxies have 2 possible attractors. If they're closed and dissipative, non-dissipative, they will form NFW or ellipticals. And if they are disk and they're open with gas, they will satisfy this kind of reaction diffusion. And I draw your attention to Eunice poster, which is an example of calculation of how small scales can impact diffusion coefficient, which enter this reaction diffusion equation. And this is my last slide. Thank you.